right, so this is podcast 9.3, which we're going to start talking about the stoichiometry that we can do with these gases we've been talking about. Now, there's actually a couple different variations of stoichiometry we're going to do in our packet, and that's actually going to happen on pages 12, 13, and 14. And we're actually going to start by looking at page 14 and doing that stoichiometry today in this podcast. And we'll cover the shortcuts that we can take to make this easier on pages 12 and 13. But I think actually doing it this way is going to make a lot more sense, because what we're going to learn here in this podcast can actually work for every single type of gas stoichiometry problem. It's just that sometimes you don't have to do all of this work. Sometimes there are some shortcuts we can take if you recognize them. So we'll talk about that in class, but this method for working out any kind of problem will always work no matter what. So if we look at page 14, we've got a stoichiometry problem there, just straight right there at the top. And one thing I want to remind you about these stoichiometry problems is that they're always going to have a chemical reaction written next to them. This is always going to get used in our stoichiometry problem, or the balanced form of this equation is going to get used in our stoichiometry problem, because that's what stoichiometry is, using the balanced coefficients from this balanced equation in order to convert between substances. So in all stoichiometry problems, when you see a chemical reaction involved in a problem, when you're reading through that problem, it's really important that you try and figure out which two substances the question is giving you information about and asking you about, finding that given and the unknown. Because once you read through, like here, it's asking us what's the volume of chlorine gas. We're going to be using that chlorine in our problem. Measured at this temperature, pressure, are required to react with 0.5 moles of silver. So we're talking about silver and chlorine. Even though they're going to come together in this reaction to make silver chloride, we don't actually care about the silver chloride at all in this problem because it wasn't mentioned in the problem. Every stoichiometry problem, every problem with a reaction is only ever going to mention two substances, and those are the two substances that you're going to need to use the numbers from that balanced equation in our mole ratio. Remember, those numbers in our balanced equation always represent moles. So 2 moles of silver equals 1 mole of chlorine. And no matter what else happens in this problem, we have to use that mole ratio to help us solve this problem. So what it really comes back to is looking at all this other information that they've given us around the silver and chlorine names, and figuring out how can I get to moles? Because we've got to have moles in order to be able to use this mole ratio. And in this first problem, it's actually pretty easy to find moles because they're sitting right there in our problem. So if we have moles, that's going to be the number we're going to start with. And we're going to jump straight in to doing some stoichiometry work. Because we got moles, we can use this mole ratio. And since we've got silver moles on top, we're going to take the silver number from that balanced equation, which means that 2 moles of silver going on bottom, and then 1 mole of chlorine can go on top. Every single stoichiometry problem is always going to have at least one step where you have to do this mole ratio. But if we look at what this question is asking for, it's asking us to find volume, which is not something that we necessarily can solve for in stoichiometry. We'll teach you in class how we can actually get to volume with stoichiometry next class. But at this point, we can't do any more stoichiometry. So this is as long as our stoichiometry process is going to have to be. We have to do that mole ratio, but that might be the only step that we have to do. We're going to have to stop and solve for these moles of chlorine, which would be 0.25 moles of chlorine, in order to be able to find the volume. And you might be wondering how we can get to volume from moles. Well, remember, we don't just have moles. We have a temperature and a pressure up here. So if I know that my temperature is going to be 290 Kelvin, my pressure is that 0.95 atm number, I have my moles, which is N, and I'm looking for volume. Well, this is going to mean that we need to use that PV equals nRT. equation. That's the equation we use when we have one of each thing that we need to solve for one of the missing values. We've done this type of problem all the time. The only thing that's a little bit different and special, kind of like when I gave you grams in those ideal gas law problems, we had to turn those grams into moles to be able to use them. Here, we just had to change the moles of silver into moles of chlorine so we could find the volume of that chlorine. We just had to get the substance to match instead of the units. So, solving for volume is pretty straightforward. We do opposite over neighbors, so nRT over P. So we're going to take that 0.25. ATM means we'd have to use the 0.0821 number as our R, and then 290 all over our pressure. And when we do that, we get a volume of 6.29, and it keeps going. But we would want to just keep 2 sig figs here because our mole number was 2 sig figs. And of course, this volume would be measured in liters because every volume that we put in or get out of that ideal gas law equation is always going to be liters. So hopefully that wasn't too tricky. It's just a little dimensional analysis, technically a little stoichiometry because we have that balanced equation. But just solving for moles, plugging it in just like we've done in the past, just slightly different. So if we look at question 2, this one is going to be very similar because it's still asking us for volume. We're looking for the liters of carbon dioxide. Oh, we need our balanced equation. You have it written out. I needed mine to pop up. And I've gone ahead and balanced that for you. So this is asking us how many liters of carbon dioxide. So we know we're going to need that 16 moles of carbon dioxide somewhere in this problem at 27 degrees Celsius and 560 mmHg can be produced from the combustion of 65 grams of octane. So octane is this C8H18 stuff. So somewhere in our problem, we're going to be using this 2:16 ratio. But reading through this problem, we weren't given moles, so I'm not ready to use my mole ratio quite yet. And as I'm looking at all the numbers that I've got, the easiest and really only way that we can get to moles right now is from these grams. If we've got grams, we can turn those into moles with a little bit of help from our periodic table. So that grams number is going to be the number that I start with. And we've got to turn that into moles so that we can use this mole ratio that we know we're going to have to use. So I'd need to add up the mass of C8 and H18 and put it all together. That ends up being 114.232 grams of C8H18 for 1 mole of that same stuff. And now that if we stopped and calculated, we'd have moles. I don't have to stop and calculate because I know as soon as I've got moles, I can use this mole ratio. And since I've got my C8H18 on top, then I'm going to put those 2 moles of C8H18 on bottom, and then the 16 moles of CO2 on top. And if it was asking me for the mass of CO2, then I could go one more step, use the periodic table to turn that CO2 moles into the mass. But that's not what it wants. It wants volume. And once again, we don't currently have a way to get to volume, to get to liters from moles in our stoichiometry. So that means I've got to stop my stoich and calculate my moles. Just like in the last problem, if we need to get to volume, and we've got moles as well as a temperature and a pressure, then we can solve for these moles, which I believe turns out to be 4.55, and use this as our N as we solve for volume, just like last time. So we're going to put that 4.55 in here. This time, because we had mmHg as our pressure unit, we need to use that 62.4 number as our R. And the 27 degrees Celsius is going to be 300 Kelvin. And then, where is our pressure? I know I found it a second ago. Ah, there we go, 560. And when we do all of this multiplying and dividing, we end up with a pretty big volume, 152.1, but I would want to keep this to 3 sig figs since I've got several 3 sig fig numbers in here. And just like the last problem, we'd put liters on that answer. Okay, now this next question is going to be a little bit different, but the process is still the same. As we're reading through it, we're going to pay attention to our substances. So it's asking me what mass of potassium chlorate, and be careful, chlorate is this KClO3 thing. This other KCl thing is potassium chloride because it doesn't have one of those special funky groups from the back of the periodic table on it. So what mass of potassium chlorate would be needed to produce 11.2 liters of oxygen? And so we care about that oxygen as well at 50 kPa and 37 degrees Celsius. So we're going to be using this 2 to 3 ratio somewhere in our problem. We've got that mole ratio ready to go. But when we're looking at this problem, we don't have grams and we don't have moles. So we don't have the normal ways that we would have normally gotten to moles using stoichiometry handy. But if you notice, kind of like the last few problems after we've done some work, we do have a volume here, we do have a pressure, we do have a temperature, and so we can actually use that P, V, and T along with an R to solve for moles. We're just going to be solving for moles using the PV equals nRT equation. We're going to be solving for N now to get the moles that we need to plug into that balanced equation and do our stoichiometry. So when in doubt, we know we're going to need to use this mole ratio. We know we're doing stoichiometry. However you can, you need to try to get to moles. So this is the only way we can get to moles in this problem. So N is going to be equal to PV over RT. And our pressure here was 50 kPa. Our volume was 11.2. And our temperature is going to be 310. Oh, and I need my R value as well. What units do we have? kPa, so that's going to be our 8.31 along with that 300 Kelvin. That's going to be going down there. I'll go ahead and cross out that temperature and say equals 300 K. Just to kind of keep track of that. I know you're used to me making those kinds of notes. And when we put that all together, that tells us that we have 0.217 moles. And it's really important right now that we don't try and say that this is our moles of potassium chlorate, because all of this information we were looking at, this volume, this temperature, and this pressure, was all about how much oxygen we had, the conditions of that oxygen gas. So the moles, when they come out of this equation, are moles of oxygen. And of course, we're going to need to turn those moles of oxygen into moles of potassium chlorate, like we always do, because we've got that mole ratio. So because oxygen is on top, we're going to put the 3 moles of oxygen on bottom, and then the 2 moles of potassium chlorate go on top. But we're not done, because even though we've used our mole ratio, notice that it asked us what is the mass of potassium chlorate. So I need to add one more step here in order to turn these moles into grams. And if we add up KClO3 from the periodic table, that ends up being 122.548 grams per mole, of course. Keep in mind, that's how many grams we have for 1 mole. And since we have the moles part of things up on top here, we're actually going to start, if we're filling in from the bottom, by putting the moles on bottom. But one way or the other, we just need that grams number to fill in the top so that we can get to the mass of potassium chlorate. So this is our stoichiometry setup, and if we multiply and divide across the top, just doing this math now that we have those moles from our ideal gas law, then we can find that this final mass of potassium chlorate should come out to be 17.7 grams. So this last problem on the page, I want you to try. And let's go ahead and cross out the words over water and cross out that partial pressure at the end. Technically, we would need to do some subtracting with our pressure, but I don't want you to have to worry about that. I don't want to add any new kind of weirdness to this problem apart from what we've already done. So notice this is asking for grams again and giving us some volume, temperature, and pressure. So this is going to get worked out a whole lot like that previous problem. And I will go ahead and balance this equation for you just to make sure you have that. I don't need it to be perfect. I just want to see you try this, but there should be no reason why you can't use your current stoichiometry skills and a little bit of ideal gas law stuff to solve this problem. If you're doing it right, it should be about 10 grams. If you are doing it wrong, then you might end up with something like 5 grams coming out, and that's a simple problem that I can kind of fix and help you see what you're doing wrong. It's a classic mistake, but it happens. I can help you with that. If you're getting anything but 5-ish or 10-ish, there's some much bigger issues, but not a problem. I want to know what those issues are when you come to class. So even if you're working it out wrong and you're not getting 10, don't erase all your work. I'm going to stamp your page as long as I see some kind of work there, and I can tell what kind of mistakes you made based on the work that I'm seeing there. So give it a try and let me know in class if you need any help.